let's take a look at some of the data you'll collect today and how to record that and do some of the data analysis and calculations later in the lab. So you are going to view the video associated with this lab, and from that video you're going to collect raw data. And one thing that you'll see here on the data collection and analysis, make sure you put your name on there. So you'll have to turn that in with your name on it. You won't really have a partner. So the data you're going to collect from the video is just for acetone. We only filmed data for acetone. So you'll watch the video and follow the instructions there. The other data that you're going to collect, ethanol, and the data for water. So this data is on a handout. So that's raw data that you're going to collect. And from the video, you're going to be given this data. There's a separate file for you just to download and copy into your lab report. Now, the next thing that you're going to have to do, and you'll notice when you collect this data, you're just collecting the volume of water or the liquid in a tube versus whatever temperature it happens to be. And then we're going to have you make a graph by hand. But that is not going to be what you're actually going to graph. You're not going to graph temperature and volume. What you are going to graph is some manipulated data. And it's very important that you carefully read through these instructions right here to tell you how to manipulate the data. And so I just want to walk through with you using this data right here, how we got that. So here's some example data. And let's just imagine that this happens to be data for water, and I'm going to put the results down here in this data table. So you're going to end up doing exactly the same thing, and if you're having trouble when you're doing the lab report, come back to this video and check this out. So what we're interested in graphing actually is how much the volume of the liquid changes for every interval of temperature change, or for every change in temperature. So if you remember back, hopefully, that you've learned that the abbreviation for change in a variable, change in something, is abbreviated by this triangle, which is called delta. So that's the Greek symbol delta. So instead of writing the change in volume, so the change in volume, which is a lot of words to write down, we instead write delta V. Now the thing that's important is when we measure variables, we always have to carry with it the units in which we made those measurements. So in this lab, we're going to look at changes in volume in milliliters. So you want to make sure that you're not telling another person, you know, you measured change in volume in milliliters and they thought it was gallons or liquid ounces or something like that. So what we want to determine or figure out is, what is the relationship between the change in volume of a liquid and the change in temperature of that same liquid. So here we've got the makings of a correlational graph. How does one variable change with another variable? So again, this is not, getting kind of crowded in here, the volume of the liquid versus the temperature of the liquid. So we don't just want to know what's the volume at this temperature, what's the volume at that temperature. If you think about it, there's a reason why that makes a lot of sense. So the volume at any particular instant of some liquid really depends upon how much you put into the container. You might do this experiment with just starting out with 10 milliliters of water. You might also do this experiment starting out with 5 million gallons of water. And so it doesn't really tell us a lot about water itself if we just measure the volume and the temperature. What we really want to know is if I change the temperature by some incremental amount, delta T, what's the resulting change in volume of the liquid, delta V? And that is something that is going to be a representative characteristic of a particular substance. That's an intrinsic property of that substance. Water will always change its volume a certain percentage with every change in temperature. So that's what we're interested in graphing. And so how will we get that data from the raw data? So what you'll want to do is look up here and follow the instructions very carefully, like it says here. And I even did an example for you in the lab. Let's imagine we've got some data for water down here, as shown in this data table. So I've moved the data table and the results table here that you're going to use onto a whiteboard that I can write on. So what you want to do is calculate a delta T and a delta V over here on the right based on the information that comes from this raw data. And the way that you're instructed to do that is to go into your data and look at the lowest temperature and the lowest volume and label those as TL for T lowest and VL for V lowest. And that's what you've got right here. And then the idea is to find the change or an interval between all the other temperature ranges and the lowest one. In other words, you'll be finding a temperature difference between those two readings and these two and these two and those two. And you need to find the corresponding change in volume between these two and these two and those two and those two. So let's do the first one. I'll do it in green. Just rewrite over that. That's this green data pair. So the delta T for the green will be 20.5 minus 14.0. And I am going to get down here 6.5. So remember the rule for significant figures. When you add and subtract, it's all about where the uncertainty is. So each one of these has 3 significant figures, but remember the uncertainty is in the last digit, the first decimal place, and they're in the same place. And so when you go down to the answer, you round to the leftmost place or the least uncertain digit that you have in these two, and that's in this position. So our answer in the table for delta T, let's call that delta T1, is going to be 6.5 degrees Celsius. So we started out with 3 significant figures in our readings, but when we calculated the difference, this reading only has only has 2 significant figures. The important thing is, what's the precision of the instrument? The instrument is only precise out to the 10th of a degree Celsius, and so that's what we're reporting. So it's not how many figures there are in this case, it's where was the instrument that we used, where is its precision. All right, let's do the delta V1. That's going to go with it. Delta V1 will be the difference in these 2 corresponding volume readings. And so that is going to be 0.420 minus 0.380, 40. And let's look at significant figures there. Again, when we subtract, it's where is the last significant digit? Where is the uncertainty? So that pipette read out to the tenths, hundredths, thousandths place. And so the uncertainty is in the third decimal place. And it is for both of them. So when you subtract, we're going to keep that third decimal place. So this would be bad, and I'll write it in red. That you would never record as 0.04. Because this number has 10 times worse precision than this number. We know this one out to 3 decimal places to the thousandth of a milliliter. This number we only say that we know out to the hundredth of a milliliter. That's 10 times worse precision. You do not drop trailing zeros after a decimal. So I can go back in here and write that out, 0.040 milliliters. One other thing I want to point out to you as a habit you should get into is to write the 0 at the beginning of a number that looks like this when there's a decimal. Because a lot of times when people are writing down things or typing it, you don't notice if you write, for example, here's a number 0.326, and a lot of times when you're typing, you might miss that decimal place. So this thing down here is often called a locator. I think it's a 0. Locator 0. It locates the decimal place. So forget this. Write the 0 down. So when we do this now, we should notice in our table of delta T's and delta V's that we're all written to the same precision, and we're going to look to see if you actually did that. And one of the things to be graded on is to maintain a consistent level of precision when you do these calculations. Let's just do one more. Let's do this last one. And it doesn't really matter. You don't have to pick these pairs. You can pick any two pairs. You just need a delta T, for example, and a delta V. And that's the data you're going to plot. But your graph is going to be the most spread out if you do it in the way I illustrated up here. So let's just do an example of delta T2. And here we've got 42 minus 14. So I'm not being sloppy, I'm writing all the information out. And this gives me, sorry, that's a 20. So again, it would be bad to write 28. Our whole point in science is to communicate how much we know about something, what our level of knowledge is. This is a lie. Right? You're lying to the reader and saying this could be 27, it could be as much as 29. You're saying you've got a lot of variation, there's a lot of uncertainty. Don't lie. When you write a number like 28.0, you say, well, it could be as high as 28.1 down to 27.9. Look at the difference in precision. We know that this value here has a very much smaller range of uncertainty than it does down here. So we're going to write that down, delta T, since this was the biggest one, I'll put it down here, 28.0. You have to report that 0. And if I do the other calculation, do it over here, delta V2 is 0.610 minus 0.380, 0.32, so 0.230. So you're going to have a new data table that has delta T and delta V values in it, and that is what you're going to use to make the graph. Now, if we advance in your lab report, you'll notice that we've put in an example of the expectations of what we want you to be able to do by hand. And so there's a lot of things in here that you want to make sure that you talk about or cover, as discussed in that video that you watched. You need to have a title. You've got to have axes that have both the unit that's being measured the quantity that's being measured, in other words, the change in volume, and the unit that's being measured. So this has to be the quantity and its unit. Quantity, unit. You've got your three lines up here. When you plot your raw data, it's a very good idea to make a dot on the screen. And then oftentimes we draw a little circle around it. If you really wanted to get into this, the length and width of the circle is supposed to represent the amount of uncertainty in the X and Y variable. Well, that's for another day, another class. We're just going to draw little circles that helps us not lose them on the paper. And you put the dots on the graph, and then you grab a ruler. You do not do this freehand. And you draw a line using a straight edge that goes between the data. And the concept is when you draw the graph, you try to get approximately an equal number of data points above the line and an equal number of data points below the line, roughly. And you want to minimize as much as you can the space between the line and the data points. And so there's actually a math formula to do that. It's called the method of least squares. The idea is to minimize, if you added up all the distance between the line and every dot, the best line would be the one that has the lowest total sum of distance between the line and all the dots. So get a straight line, split the difference. The idea is, and this is a really key thing. So here's a rough sketch of me drawing a line in green between a set of data points. It is not drawn with a ruler, but I want to just make the point about how you draw the best fit line. You'll notice on here that I have tried to sort of split the difference between these data points and the line so that on average there's an equal number of points that are a distance above and below the line. What is the reason for this? Why would we never connect the dots? Do you know? Well, the reason is because every data point is an estimate. Remember, because it's a measurement, it inherently has error associated with it. So the more precise we happen to be, the closer our estimated dot here, the measurement that we made, is closer to reality, perhaps. That might mean it's more accurate. The precision means, well, every time you repeat this, would we always get the same measurement for that data point? Or another way we could also look at it is, where do all our points lie very, very close to the straight line? That means we were able to make repeated measurements with the same degree or a level of error, very small or very large. The accuracy really tells us how close are we to reality, which we may never know what reality is. So the point of the matter is, every one of these things is an estimate. And with every estimate, every measurement, we can't say for sure that this is the real value of the y variable at this x amount. And so what we're trying to do with the graph is say that, well, sometimes our error is on the high side, and sometimes our error is on the low side, right? If it was just a random error or random mistakes when you make a measurement, we would expect if you did a lot of them, half the time they would be high and half the time they would be low. And so this line sort of averages out the highs and the lows and gives us a really good guess based on statistics of half being high and half being low approximately. It's our best estimate. And so that's the reason why we never connect the dots. So now when you look back here, there's a couple other things you have to make sure you have when you do the graph, you need to have a key. You just can't draw a bunch of lines. If you want to do it at home and you've got some colored pens or colored pencils, and by the way, you should always make graphs in pencil because you're going to make mistakes and you're going to want to erase. You don't want to have anything scribbled. You see how nice and neat this was? This was done in pencil. But you need a key to tell which line is which. And oftentimes, if you don't have colors, you can differentiate it by the what we call point protectors, the box or the circle that you draw around the points. And so that tells me which line belongs to which particular substance. So other things we need you to make sure you complete. Make sure you complete these pages, fill in all the boxes here as you're preparing your graph to make sure that you get it right. Here are some checkpoints to make sure that you are going to get your graph correct. And then there's an extra sheet of graph paper in there for you, just in case you make a lot of mistakes. And then there's the post-lab analysis. And in that post-lab analysis, that's where you're going to do some extended calculations to let us know that you kind of understand what's going on here. And so one of these is to figure out a slope calculation. And I want to go through that for one of these just to make sure you understand how to do that. So the next part is to do the slope calculation. So just wanted to remind you, if I went back and looked at our little graph that we drew before, the data points, and I had a line going through it. When you calculate the slope, never use your actual data points. And why not? It's as we discussed before. They are fraught with error. They're made with inherent error. The best guess of the trend, which is what we're looking for, is to pick 2 points that are on the line itself. So we expect that the 2 orange data points are better representative of the actual data than any one individual data point, right? So if you did a poll of the population of the United States and asked them, who do you think is going to be the next president, or who do you want to be president? If you had just picked one person or 2 people, that would be a sample that has lots of error, right? It could be, they could be anybody. They could say Bugs Bunny, I don't know. But if you picked a large sample, then we get a better feel for the trend in the data. And so what we want to do is take a slope where this is going to be the change in the y variable. What was the y variable? The y variable was delta v. And what was the x variable? It was delta t. So the slope is going to be the change in the y variable. Wow, that looks pretty weird. Divided by the change over here. This is going to be delta, the change in the x variable. What's the x variable? Delta t. So now the slope of this line, let's do black. The slope is the change in the y variable divided by the change in the x variable. So what we need to do is find out what are the values of the change in volume and the change in temperature, the change in those from some points on the line. And so what I did is generated some points. I went back to a graph and I took data points from the line. I read it physically off of the graph. I read the x and y value for each one of these and read it off the graph, and I got them here. So here is not a temperature, but a delta T value of 7.7. 7.7. And that had a corresponding delta V value from the graph of 0.306. And that's my first data point. And I did the same thing for my second data point, and I got these two. So now I want to do a slope calculation. And this is where we have to pay attention to significant digits. All right, so our slope has got to be the change in delta V, which is delta V2, oops, erased it, minus delta V1. So that's going to be 0.099 minus 0.306. And we're not going to worry about the negative sign because it'll work out when we take the ratio. So 0.099 minus 0.306, that comes out to be negative 0.207. Now I need to calculate the change in the x variable, delta t, and that is t2, delta t2 minus delta t1, or 2.8 minus 7.7. So 2.8 minus 7.7 comes out to be negative 4.9. And this is in degrees Celsius, and these are milliliters. So my slope is the change in y over the change in x. And so the change in the y variable was negative 0.207 milliliters. And the change in x is negative 4.9 degrees Celsius. So you see how nice the negative signs cancel out. So let's do the math. 0.207 divided by 4.9. This comes out to 0.422448898 milliliters for every degree Celsius. That's way too much precision. I got that off my calculator. Another common mistake. Now I have to figure out how to round this thing down. So now it's multiplication and division. And in that particular case, we just actually can erase that. All right, so multiplication and division is how many significant figures are there in each of the values. And so this one has 3 significant figures, and this value has 2 significant figures. And so we choose our answer to have the same as the factor with the fewest. So our answer can only have 2 significant figures. So I'm going to report this, 0.42 milliliters per degree Celsius. So go back up to our table, 0.42 slope units, milliliters per degree Celsius. So your slope calculation, you can probably do it in here, or if you need to write it on a separate sheet of paper, you can include that too. But the idea is you're paying attention to significant figures. By the way, these should be delta t. Okay, so there's some other hints over there. If you happen to have zeros for any of these, don't drop your zeros at the end. That's kind of an important point. All right, on the next page are the last couple questions. And this first one up here says, what is the y-intercept? So our goal is to make the equation of a straight line. That's the trend. That's the relationship between delta v and delta t. So we got to get the y-intercept. This is something, there's no calculation involved. We're just going to go back to the actual graph. And you have to figure out, let's see if I can make this big, by getting down with your eyeballs and look at, for example, where does the line cross the y-axis when x is 0? That's where you're going to look. Where's x 0? Read up. Here's the line. What's the value of y for that line when x is 0? That's the y-intercept right there. And so whatever this is, this value, that's the y-intercept for that line. This got kind of messy in here, but this line looks like it crosses the y-intercept right over here. So you just read that off the graph, and then that goes back in that table. Let's go back to the table. So if your line you think goes through 0, you would report 0.000 milliliters. Why so many zeros? That's the precision of the tube. The handwriting is atrocious. That's the precision of the tube. So it would not just write 0. And you should notice that I also need the units in there as well. Okay, let's make up some numbers. Let's say that I didn't want it to be 0.00, but it was something else, 0.12, just for the sake of argument. Because then we're going to use all that information down here to write the equation of a straight line. So remember, a straight line is y equals the slope times the x variable plus the y-intercept. In science class, the x and y variable are things. In algebra class, they're just x and y. Those are called dummy variables. But these are not dummies. These are real physical quantities. So when we write the equation of the line, instead of writing x and y, we are going to write the variable. Another thing that confuses students is do not put numbers in here. This is the general relationship. How is delta V in milliliters related to delta T in degrees Celsius? That's what the numerical value of the slope that you calculated and the y-intercept that you calculated are going to tell us. So in bold, that's where the values go. Delta T and V are the two things that we were making measurements of. I need to save myself some room down here. And let's do it. So for water, the volume change in milliliters is related to the slope. Well, let's see, what did I write for the slope? It was 0.42 milliliters per degree Celsius. So 0.42 milliliters per degree Celsius. That's the slope. Y equals slope times x variable, which was delta t, plus our y-intercept. What did I say that was? 0.012 milliliters. And that's it. That's the relationship for water between its change in volume dependent upon the change in the temperature in degrees C. So the key here is just remember how we are always for the rest of your life in chemistry class. You're going to write the equation that looks like this. No numbers. Those are the variables of study. The y variable, the x variable. Do yours include units? This is the slope, and that's the y-intercept. That's the data. This is the experimental data. That's the relationship you determine by carrying out the experiment. So the concept here is that this is a real equal sign. It really, really, really means equal. And so whatever's on the left-hand side is exactly the same, not sorta, exactly the same as whatever's on this side. So if there is milliliters on the left-hand side, then you can always check your equation. All your dimensions had better come out to be equal to milliliters, because milliliters has to be milliliters. It can't come out to be, grams or something. That's ridiculous. So let's see. A milliliter per degree centimeter, milliliter per degree Celsius times Celsius, those cancel, and you're left with milliliters. That's the result of those two units. And the y-intercept, that's a y variable, milliliters. A milliliter is a milliliter. The volume change in milliliters is equal to this number of milliliters. That's what it tells us. All right, that's what we're going to be looking for when we grade this report. And we are going to let you answer some questions on your own. And so you should turn this lab report in at into D12 by the beginning of your next lab period next week.